This is part one of 5 parts of hypothesis testing. In this one, we're going to cover the basics, which means we're going to cover the overall process of hypothesis testing. Hypothesis testing is a process. And what we're going to do in hypothesis testing is we're going to say something about the population by looking at a sample. So we're using what's referred to as statistical inference. With hypothesis testing, we can assess the probability or the likelihood that statements about a population are true. We can never say that they are precisely true. We can just say something about the likelihood that they're true. And this is an important distinction when you look at any type of research and analysis that involves hypothesis testing. It's a 7-step process where you have to state the hypotheses, identify the test statistics, specify the significance level, state the decision rule, all before you touch the data. All before you start calculating means or variances or whatever you're calculating, you have to set the stage. And you set it up where you say, okay, this is what we're going to test. This is how we're going to make a decision. Then you collect the data, do your calculations. Then you make a statistical decision and then an economic or investment decision based on that. What we want to do is set out hypotheses, and there are 2 hypotheses, the null and the alternative. Now with the null hypothesis, this is what we want to test, or another way to look at it is this is what we want to reject. The alternative hypothesis is dictated by the problem at hand, and you'll see that in a moment. Basically, the null and alternative hypotheses need to be mutually exclusive and collectively exhaustive. Now I'm just going to use theta here to represent any old population parameter, and theta naught to represent the hypothesized value. Now, when we get into the testing, we'll have mu for mean, sigma for standard deviation, and so forth. Right now, let's just use a generic theta. And we can specify hypotheses as 2-sided alternatives, which is in number 1 here. So you have a not equal to in the null and a not equal to in the alternative. Or you can have 1-sided alternatives, as in the case of 2 and 3 listed here. In the case of 2, the alternative is a greater than. In the case of 3, it's less than. Now what you'll see is the null completes the picture. So if the alternative is greater than, the null is less than or equal to. If you have a greater than or less than in the alternative hypothesis, then you're going to be focusing on a single side of the distribution. That is, you're going to have a one-tailed test. If you have not equal to in the alternative, you'll have a 2-tailed test. And the whole idea of setting up these hypotheses is that you need to be complete. That is, you've got to cover the entire ground with these 2 hypotheses. Now there is an approach that you'll see if you start Googling around and looking at hypotheses. You will see an approach that has the null as always being what's called a simple hypothesis, which is an equal to instead of a greater than or less than in there. And that you'll find about half the stat books are like this. You'll find that my habits are such that I'm used to doing the simple null as well. When you do the simple null as an equal to, when the alternative is a greater than or less than, you're saying that the other cannot happen. So if you say the alternative is a greater than, and you specify the null as equal to, you're saying that values less than just won't exist. It just won't happen. So you're complete because you've covered all possible grounds or reasonable grounds. So you will see hypotheses stated this way, and it's usually someone who is a purist in terms of specifying hypotheses. Because when we get down to the actual testing, all we can test is equal to a specific value, not equal to a range of values. So the purists that like the simple null that is the equal to, even when you have an alternative which is one-sided, it's actually more correct. but our textbook uses the other, so we're going to go with that most of the time. So in our hypotheses, we're going to dictate either a one-tail or a two-tail test. And if we have a less than alternative, what we call the rejection region will be on the left-hand side. If we specify greater than, the rejection region will be on the right-hand side. And if we specify not equal to, the rejection area will be both on the high side and the low side. So you can see that in the three diagrams here. Now, how do you know how to set up those alternatives? Well, it'll be dictated by the problem at hand. That is, if there's something in the economic or financial theory we're testing that it hints at larger than or less than or greater than or fewer than, then we start having a one-sided alternative. If the question is simply asking whether something is equal to something, it's two-sided. So the problem is going to dictate the alternative. So here's some examples. Test whether the average corporate tax rate is less than 33%. So you see those words less than 33%, then you know it's a one-sided alternative, less than 0.33. So therefore the rejection area will be on the left-hand side. Test whether the volatility market during the financial crisis is greater than the pre-crisis. So you were talking about volatility, so we'll look at variances and we'll make the comparison. The alternative is the crisis variance is greater than the pre-crisis variance. That leaves everything else in the null. We can test whether a relationship between the stock price and the purchase of stock by non-management employees of the company. We're talking about a correlation in this case. There's nothing in terms of greater than or less than, any relationship like that other than is there a relationship? So in this case, the alternative is not equal to, and the null is the simple null equals 0. In the last case, test whether the stocks in the Dow Jones Industrial Average have better Sharpe ratios than the stocks in the Wilshire 5000. We basically are dictating that the alternative, that the mean for the Dow Jones Industrial Average is greater than that of the Wilshire. So again, the problem description will dictate the alternative and what it looks like. Then you identify the appropriate test statistic. Kind of the generic way of looking at a test statistic is you're comparing the sample statistic with the population parameter and you're adjusting for the variability in the sample, in most cases the standard error of the sample statistic. In the case of testing a mean for a population, if we know the variance, then it's the equation on the left-hand side with z distributed. If we don't know the variance, then it's the t distributed on the right-hand side. But we compare the sample value with the hypothesized value and divide by the appropriate standard error. Now, you'll find that we don't know the variance of the population more often than not, because if we knew the population variance, then really there's very little need to do any testing here or sampling. So we're going to be focusing on the right-hand side equation most of the time when we're testing the mean. Now, there are different distributions depending on what we want to test. The t distribution is the one we're going to use the most, but don't forget about the other distributions. We have a z distribution, which is the standard normal. We have the f distribution, which we use when comparing variances, and we have the chi-square distribution when we're testing a single variance. The t distribution will approach a normal distribution, but never quite get there as the degrees of freedom increase. Both the f and the chi-square distribution, as degrees of freedom change, the entire shape of the distribution changes. So you can see them change depending on degrees of freedom, and sometimes they may even look almost normal. Often they're not. They're going to be truncated at 0, so they're going to be positively skewed distributions no matter what. Now we're going to have errors in hypothesis testing. Remember from sampling, if we take a given sample from a population, chances are pretty good that the sample mean will not be exactly equal to the population mean. No matter how good a sampling technique we have, unless we sample every observation, a given sample is not going to have the same value as the population parameter. So we're going to take some risk. So we take some risk, and that risk that we take as decision makers include the type 1 error, which is the risk that we'll reject something that's actually true. It's also called our alpha. Type 2 error is a different kind of error. Here we don't reject when we should have, when the null hypothesis is false. So, in one case, if we mistakenly reject the null, we make a type 1 error. If we mistakenly fail to reject the null, we make a type 2 error. So these are mutually exclusive. But type 1 and type 2, they're both types of errors. You'll also see in this chart correct decisions. You'll see pretty soon that the correct decision for the true failing to reject and true null is our confidence level, and our correct decision when the null is false is the power of the test. So the level of significance is what the researcher decides, how much risk they're willing to take that they're going to be wrong in terms of rejecting something that's true. You're going to see it referred to as alpha, and then use the Greek letter alpha, and so forth. The level of confidence and the significance level are related. They sum to 1, so they're complements. So that means if you increase the level of significance, you decrease the confidence level, and vice versa. So you need to be aware of this as you're constructing your tests. Now there is a trade-off. For a given sample size, if you increase your type 1 error, you decrease type 2 and vice versa. The only way of decreasing both type 1 and type 2 errors is to increase your sample size. The power of the test, that's correctly rejecting a false null hypothesis. That is what we would like the most powerful test. So we want something with good power. So we're going to choose a test statistic that is most powerful. So for the case of testing a mean, we're going to choose a particular t-distributed test statistic because that is more powerful than an equivalent non-parametric test. So because it has more power, we're going to prefer that. Now in terms of stating a decision rule, you lay it all out, then you gather your data. So you lay out and find the critical values. If you have a two-sided alternative, you'll have two critical values, a positive and a negative. If you have a one-sided test, you're going to have a critical value on the side where the tail, rejection area is. So if you have a less than alternative, then the critical value is going to be on the left-hand side at the edge of that tail. And then if you have a greater than, it's going to be on the right-hand side. Now, we're going to take that level of significance. If you have a one-tail test, all that alpha, say 5% of area in the curve, is going to go in that tail. If it's two-tail test, we're going to divide it by 2. And this is very important and often overlooked when you're in the midst of doing tests. But if it's one tail, all the alpha goes to one tail. If it's two-tail, it's split between them. And this is important when you're using, say, tables or even your calculator to come up with critical values and rejection areas and so forth. Now, confidence intervals. If you have an alternative hypothesis that's two-sided, you can do the same thing that we're doing with hypothesis testing with the confidence interval. And you already know how to form a confidence interval. So in the case of the mean, you would take the sample mean, and then you plus and minus the reliability factor, which in this case would be a t, for alpha divided by 2, because it's two-tailed, times the standard error. Well, you'd set up this interval. And if the hypothesized value is outside of the confidence interval that you've constructed, you reject the null. If it's within the bounds, you fail to reject the null. So it's another way of performing a test. The next step is just to collect the data and calculate the test statistic. You do have to keep in mind all the sampling that we learned before, and you want to make sure that you have a good sample. So you want an unbiased sample. And then you make a decision. And the only two things you can do, you can either reject the null or fail to reject the null. You can never, ever, ever accept the null hypothesis. And there's no such thing as almost or barely. It's cut and dry. So you have to look at your critical value, then you look at your calculated test statistics, see where they are in relation to one another, and you make a decision. There's nothing that's almost significant or anything of that nature. And then you make an economic decision. There's some times when there may be something that's statistically significant, and yet economically it wouldn't make sense to do. So you do have to look at the economics of what's going on as well. Whether that's putting together a portfolio that has certain characteristics that you think are going to be profitable, whatever that decision is, you've got to keep in mind the economics of it, whether it's trading costs or anything else that might enter it. Or maybe it's so small it isn't worth your time. Now, I do mention parametric and non-parametric tests. What we are going to focus on are parametric tests. And that is, we're going to have some assumptions regarding the underlying distribution of the data. Is it normally distributed, for example? Non-parametric tests don't worry about the assumptions at all. And they don't worry about what the underlying distribution of the data is. And so you sometimes have to use those. For example, if your data is in ranks, or you have data which has a distribution that doesn't fit any of the statistics that we have. So it is the case that you're going to have to resort to non-parametric, but you'll find parametric tests are much more common, and often they're easier to execute, but non-parametric and parametric tests are all available in the standard statistical packages such as SAS or R. And that's it.